suppose you've got two capacitors C1 and C2 which are connected in series to a battery with voltage V. What is the voltage across each capacitor? So this is a situation that comes up very often in doing problems, so I think it's good to just go over this. So I have a battery with voltage V, which means that the uh, potential difference, fixed potential difference between the two ends of the battery is V. So if the battery is a car battery always has 24 volts. Then V would be 24. If it's one of those um, AAA batteries, they have 1.5 volts across between their two ends. So then V would be 1.5 volts. So it depends on what kind of battery it is. So you've got a battery like this, and you've connected two capacitors in series with this battery, C1 and C2. Okay, so you want to find out what is the voltage across each. So how would you go about this? Well, first thing that you can do is you can replace the C1 and the C2 by their equivalent capacitance. So let's see what the equivalent capacitance of C1 and C2 is going to be. Let's call this C equivalent. So to find C equivalent, you would they're in series, so you would do 1 over C equivalent is equal to 1 over C1 plus 1 over C2. And if you simplify this, it turns out to C1 C2 divided by C1 plus C2. Okay, so for two capacitors, that is what this general formula reduces to, C1 C2 divided by C1 plus C2. So it's handy to remember this formula, but remember that this only applies to two capacitors which are connected in series. If you have more than two connected in series, then you have to use the general formula, 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3, and so on. But if you just have two, then then you can save a little bit of trouble by just using this formula. So this is the equivalent capacitance of C1 and C2, which are connected in series. So how do we find the voltage across each? What we can do is we can calculate how much charge the equivalent capacitance is going to have, right? So that you can do by just using Q equals CV. So let's call this circuit number 1, and this is circuit number 2, which is just the simplified form of circuit number 1. So in circuit number 2, uh, let's find the charge on the equivalent capacitance, right? So the charge on the equivalent capacitance would simply be um, C equivalent multiplied by the battery voltage, right? So that gives you the charge that the equivalent capacitance would have. And so that's also the charge that's held by C1 and C2, right? But we know that when capacitances are in series, they all have the same charge. We discussed that earlier. So that means Q that we just calculated is also the charge on both C1 and C2. In other words, C1 would have this charge plus Q, and other plate would be minus Q. This would be plus Q, this would be minus Q. That is because each capacitor in a series connection has exactly the same charge, right? And so their equivalent capacitance would also have the same charge. So Q is equal to C equivalent times V is not only the charge on the equivalent capacitance, it's also the charge on each of these series capacitors. Okay, so we've successfully found the charge on C1, on both C1 and C2. They have the same amount of charge Q. So from there, we can easily find out what is the voltage across each capacitor. So V1, which is the voltage across C1, you can just use the same formula, Q equals CV. V1 equals Q, the charge on C1, divided by the capacitance of C1, right? So V1 is equal to Q divided by C1. So I'm just using the capacitor equation, Q equals CV on the first capacitance. I know what charge it has, that's Q, and I'm trying to figure out what voltage appears across this capacitor. So let's plug in what we just got for Q. Did we work it out? So Q is equal to C1 C2 divided by C1 plus C2 multiplied by V. Let's plug that in. My diagram is getting kind of messy, so let me just draw this neatly over here. All right, so what we did was we had our battery V, and that was connected to two capacitors C1 and C2, which were in series. Okay, we replace the C1 and the C2 temporarily by their equivalent capacitance C equivalent, where C equivalent, as we know, is equal to C1 C2 divided by C1 plus C2. And then we used the capacitor equation Q equals CV to find how much charge is on the equivalent capacitance. So the charge on the equivalent capacitance is equal to C equivalent multiplied by V, and so that's going to be C1 C2 divided by C1 plus C2 multiplied by V. Now this is the charge on each capacitor. So this is the charge on each capacitor C1 and C2, right? So now we can we figured out how much charge there is on each capacitor. So what we were doing in the last slide before we moved here is we were calculating the potential difference across each capacitor. So V1, the potential difference across the first capacitor, would be the charge on C1 divided by the capacitance of C1. So that's just going to be C1 C2 divided by C1 plus C2 multiplied by V, this thing divided by C1. So it's just going to be C2 divided by C1 plus C2 multiplied by V. That is the potential difference on the first capacitor C1. And what about the potential difference on this across the second capacitor? Again, same procedure. It has the same charge Q, so its potential difference would be Q divided by its capacitance. So that's going to be C1 C2 C1 plus C2 V divided by C2, and so that's going to be C1 divided by C1 plus C2 multiplied by V. Let's just verify uh, what do we expect the potential difference across C1 plus the potential difference across C2 to add up to. They should add up to the total potential difference across the total potential difference, which is the potential difference of the battery, right? So let's see if that's indeed what happens. So V1 plus V2 is equal to C2 V. I'll factor out the V. So C2 divided by C1 plus C2 plus C1 divided by C1 plus C2 times V. And so that is just V. So that it makes sense. The potential difference that appears across V1 and V2 add up to the total potential difference. Now notice one thing here. Notice how the two capacitors distribute the potential difference between them. So they distribute the potential difference between them in inverse ratio of their capacitances. So the potential difference that appears across C2 or C1 is C2 divided by C1 plus C2 times V, and the potential difference that appears across C2 is C1 divided by C1 plus C2 times V. Let's look at a simple numerical example. Suppose I have a 100-volt battery. So I've got a battery that's 100 volts, and I break it up. I have two capacitors. Let's say that one of them is 2 nanofarad, or just to make the numbers simpler, one of them is 2 farads and the other one is 8 farads. How much potential difference would appear across each one? So you can see that from our formula that we just got, the potential difference that would appear across the 2 farad one would be 8 divided by 10 multiplied by 100. So this one would get 80 volts. And the potential difference that would appear across the 8 farad one would be 2 divided by 10 multiplied by 100, which is 20 volts. and so it adds up to 100 volts. So the point is that the two capacitors will split up the voltage among themselves in inverse ratio to their capacitances, right? So this fact, knowing this fact is often helpful in doing problems.